Hello, everybody. So I'm Limited Results, and I'm really happy to present some hardware exploits today, and I hope you will enjoy. So just two words about me. I'm limited by the time, the money, and my skills, of course, sometimes. I push some results here when I have time. And yeah, I come from the offensive side. I focus on hardware and low-level vulnerability. So no affiliation. So it's time to play now. So a few months ago, I decided to investigate into the ESP32. And yeah, because it's a system on chips, pretty well deployed today. It was released in 2016 by Espressif, a Shanghai company. They sold more than 100 million of devices in January 2019. They became the wireless MCU SoC market leader. And they claim to have state-of-the-art security and provide 12 years longevity commitment. So it's quite nice. Let's see. You can find this kind of platforms in IoT, a lot of different IoT today is embedding these platforms. And also on the wireless, and it can be used as a wireless peripheral to add connectivity to previous system generation. So the target, of course, is the following one, ESP32, manufactured in 14 nanometer node. Package is QFN 6x6 millimeter, 48 pins. So here are some features. I will not describe all the features of these chips, but here we can see he has an integrated modem providing Wi-Fi and Bluetooth. It's ultra low power based on Xtensa dual-core X6. This core can run up to 240 MHz. He has ROM, SRAM, but no CPU caches. A lot of GPIOs, touch sensor block, ADC, a lot of features. Also a lot of protocols supported by these IoT chips. 4 SPI, 3 UART, Ethernet, even CAN, but no USB, unfortunately. So typically, it comes with these form factors. It's a system-in-package module. The most well-known is the ESP32W Room 32. I mean, this module is very easy to integrate to existing devices. You just have to footprint the module on your PCB. It comes with an integrated flash storage under the shield of 4 megabytes. It's FCC certified, and it's very low cost, maybe $1, $2. For the test, I will use this development kit. It's the unofficial one, but I mean, it's the same. You plug that to a micro USB. You can power the entire development kit. It provides a TTI USB port, serial to USB port to deal with the chip and to program it. And then he has also some exposed headers. And it's very low cost. I mean, $15. So about the software, Espressif has developed and open source their development framework on GitHub. It's based on Xtensa ESP32 ELF toolchain, and they also provide a set of Python tools called ASP tool. And it is used to manage the configuration of the chip, to flash the firmware, to dump it, etc., etc. So quality of documentation is very good. They provide datasheet, they provide a technical reference manual, they even provide read the docs, I/O. They support Arduino, but I don't use it because it's precompiled library and I don't like it. And this chip is also an official Amazon AWS IoT platform, so you can run FreeRTOS, Mango's OS, and everything you want RTOS. So the agenda today is to focus on built-in security. To do that, I just grabbed the datasheet, and then at this chapter security, I can see 4 points. So we are going to talk about crypto hardware accelerators. We are going to talk about secure boot, flash encryption, and OTP. So it's time to start. But before to start, we need a plan. I will spend about 3 months to investigate on these devices during my spare time. My objective is to break one by one the security features previously listed. For that, of course, I use physical access because, I mean, it's easy and it's a plausible attack scenario today. For example, we can think about supply chain attacks or even the final user attacking his own devices to profit. So I will probably use hardware techniques, fault injection, side channel maybe, micro-soldering, PCB modifications, some reverse, and a code review. So 2 words about voltage fault injections, sometimes called voltage glitching. So it's a well-known, still efficient, and low-cost fault injection techniques nowadays. A lot of public resources about voltage glitching, so I will not detail a lot, so you can go to the internet for that. But the goal of these techniques is to perturb the power supply to induce a fault during critical software-hardware operation done by the platform. So we can expect effects like skipping the instructions, for example. This is typically useful to bypass a CMP instruction. We can also expect a modification of data of code. This is really useful when you have to modify branch conditions, for example. But we can also find unexpected effects because it's really difficult to predict and to understand faults in nowadays complex CPU architectures due to the cache effects, maybe due to the pipelines of the architecture. So when we talk about voltage glitching, we have to study the power domain. So here is the power domain of the ESP32. It has 3 separate power domains. Is SDIO power domain, it's not interesting for us. It's RTC real-time clock domain and CPU domain. First, we are going to focus on CPU domain, and we can see it shares 2 power signals, VDD CPU and VDD RTC. This is quite weird, but this is their design. So we can see also some low dropout regulators, LDO, in between the CPU domain and the external signals. This is to stabilize internal voltage, and this maybe can have effects against glitching. I don't know. And then in the datasheet, it's clearly specified brownout detectors is present inside the chip. And they say if the BDO detects a voltage drop, it will trigger a signal shutdown and even send a message on UART. So this can maybe detect some glitches. So I did some tests, and yes, I can see the message on UART about the BDO and the reset of the chip. But this is only effective on VDD RTC. So consequently, I will only use VDD CPU to glitch my ESP32. So now it's time to prepare the target. So I remove the shield. It's quite easy. We can see now the ESP32 in the center and near to it the SPI flash. Okay, the module is not screened, but the schematics are available, so it's really easy to reverse. I remove the capacitors connected to the VDD CPU and VDD RTC. If you can see the 2 images, you will be a diff. It's maybe 6 or 7 capacitors missing. So after that, I have to modify the PCB. For that, 3 steps. I expose the VDD CPU trace, pin 37. I cut this trace, and I connect my glitch output to the VDD CPU, and I found a GND point. So quite trivial. Then, about the hardware setups, I designed my own made glitchers. It's based on MAX 4619, which is an analog switch. I add some passive components, SMA connectors to be able to plug and unplug easily my cables. I synchronize this glitcher by a scope, and I trigger the glitch by signal generators. I send USB commands to set the different parameters, like the delay, like the width of the glitch, like the voltage. So at the end, it looks like that. I mean, it's a little setup, and it's controlled by Python scripts, and it can run during days. It's fully automatized. So when I sleep, I can glitch. So I need to verify the voltage glitching effects. For that, I probe the UART 0 because the UART is directly powered by the VDD CPU. Then I glitch, and I can see a very big glitch effect on this signal. It means inside the chip, we can expect the same effects, the same low dropout effects. So for me, the effects looks quite good. I'm quite confident now. And it's now time to make the first test on the crypto core. So crypto core is also called the crypto accelerators, crypto engine sometimes. It's just a peripheral to speed up the computation of different algorithms like AES, share, RSA. Why it is interesting to Pawn? Because it is used by the crypto libraries of Expressive, the dedicated one, but it's also used by the ARM Mbed TLS. Mbed TLS is the ARM crypto library, and a lot of IoT are using it today. My goal is to focus on the CPU crypto interface, so typically the crypto drivers. Of course, I do not expect to find a pure software vuln, because this crypto library was audited since a long time by a lot of skilled people and cryptographer. But me, I'm going to look for vulnerability triggered by fault injections. So it's time for code review. But in the datasheet first, they provide a 4-step to describe a single IES operation. So we can see the first is initialization of registers. Then you write one to a specific registers to start the IES. You wait until the end of the computation, and then you read the results from the IES text M registers. And this, when you look at that, you see a design weakness, because the registers used to store the plain text are also used to store the ciphertext. This is typically called encrypt in place, and it can be risky, because if something goes wrong during the IES call, or even during the step 3, I'm pretty sure I can retrieve the plain text directly. So this was pretty cool and simple to exploit as a first poke, and it's why I'm going to demonstrate that now. So we look at the code. It's the crypto driver for IES, and then we see the same naive implementation of the 4 steps previously described. So they used a memblock variable, an array pointer, to store the input, but also to store the output. So previous weakness is confirmed. Here we have multiple spots to trigger and to insert our fault. We can trigger IES start, for example. We can try to fault the while condition. We can also try to fault the for loop. So it's quite easy here. So as a poke, we can see on cipher number 2, the IES output is correct. But on the cipher number 3, the ciphertext output is the same than the input. So this was a very simple proof of concept. Now the vulnerability number 2 is about IES set key. Set key is a function to load the key inside the crypto core. So it has to be secure. And here we can see it's just a for loop. It's an unprotected for loop to load a very, very sensitive data. Consequently, when you target this for loop, you will change the value of the final ciphertext. And then, using a little Python script, you set the key to 0 instead of 30 multiplied by 16. And then you obtain the same ciphertext. So it means the key was set to 0. And this is good because the value of this key is now persistent until the next set key. So it's typically nice to attack IES CBC, for example. This was some of the vuln I found in the crypto core. So, as a little conclusion, the cryptograph does not improve security. I found several vulns in IES and share, expressive as patch since, embed TLS, I don't know. I went to responsible disclosure, and I didn't obtain answer from Expressive and ARM during 1 month. But during this time, Expressive tried to silent patch me, so this is not very elegant. And the bug bounty from ARM embed TLS is a fake one, so you don't receive any reward. So I decided to not share with them. But I was a little bit in a fury, and ready to pound a little bit harder now. So let's talk about the secure boot of the ESP32. Secure boot is the protector of firmware authenticity. It's here to avoid firmware modification because it's easy to flash directly malicious firmware into a SPI flash, especially when you have physical access. And the CRC today, they are not sufficient. The secure boot will create a chain of trust from the boot ROM, which is the first code executed inside the ESP, to the bootloader until the final application. So secure boot is here to guarantee the code running on the devices is genuine, and it will not boot if one of the images are not properly signed. So first, during the production, the developer has to set a secure boot key, SBK. This is burned into eFuses, block number 2. I will explain later eFuses, but it's a memory inside ESP32. This secure boot key cannot be read out or modified because the eFuses are read-write protected. And this key will be used by the boot ROM to perform IS-256 ECB. Then the developer will create a SCDSA key pair. The private key will be used to sign the app, and the public key will be integrated to the bootloader to verify the signature of the application. So the bootloader signature is the following now. We have 192 bytes headers located at 0x0 on the flash SPI layout. The first 128 bytes are pure random, and then we have a digest, 64-byte digest. This digest is the result of the hash of the encrypted bootloader plus the ECDSA public key, and these are encrypted by IES using the secure boot key, and then it is hashed to finally obtain this digest. The digest is located at 0x80 in the SPI flash layout. Now on the field, the boot process is the following one, according to my reverse. The reset vectors, located at the address at the bottom. Then the ROM starts. The ROM loads and checks the boot images using the secure boot key, loading from the OTP, from the fuses. Then the bootloader starts if everything is okay. Then the bootloader load and check the final application using the ECDSA public key. And finally, if everything is okay, the application is running using execution in place mechanism. Here we have two verification mechanisms. One is the boot ROM stage 0, which is here to compute the digest with the secure boot key and compare with the 64-byte digest previously flashed at 0x80 inside the SPI firmware. Then we have also a SCDSA verification done by the bootloader, and micro-ECC is used. It's an open source elliptic curve cryptography. So I will focus on stage 0, of course, because the signature here is based on symmetric crypto, and this is a very, very big mistake. So, and I will focus on secure boot key, of course. It's the IES used to sign the bootloader. And this is a critical asset. But unfortunately, it is protected because I cannot read out this secure boot key from the fuses according to Expressive. Now, I'm going to set the secure boot on the ESP32. This can be done automatically by the framework, but I prefer to do it manually. I burn the secure boot key inside the block number 2 using this command, and then I set the secure boot the ABS-done fuses to activate the secure mechanism. We can see the fuse map here. We can see an integration point on the BLK2 because I cannot read out this key. Okay. Secure boot is set, but I didn't burn the JTAG fuses. We will see that later because having debug is always pretty easy and pretty useful to exploit and to prepare exploits. So secure boot in action is very simple. I design a little code, so it's a hello world. I sign it using the SBK, I make flash, and then it runs, of course. Then I modify the code to do another hello world, but I don't sign it. I have no key. I flash it inside, I compile a flash, and then, of course, it fails because the verification in stage 0 is not good. And this is perfect for me. Because now I want to bypass the secure boot. Why? Because bypassing the secure boot will give to hackers code execution. Code execution on the devices is the first things to do when you hack something. How? I will force the ESP32 to execute an unsigned bootloader, and then I will load my unsigned app. I will focus on boot ROM because it's always nice to exploit boot ROM vulnerability, and it's always nice to fix. It's always difficult to fix boot ROM vulnerability. So I need to reverse the boot ROM, and first I need to dump it. To dump the boot ROM, it's very simple. I look at the memory map. I can see it, the first line. It's very simple. And then maybe you remember I didn't burn JTAG fuses. So I connect a little FTDI board to the ESP32. I use OpenOCD plus Xtensa ESP32 GDB. And I have now a full debug access. I land to the reset vectors. I can single step inside the boot ROM, so I can also easily dump the boot ROM. And it's time to reverse. I will not describe all the reverse because it's quite a painful task, but Xtensa is an exotic architecture. It has some different mechanisms than ARM and other architectures, like register windowing. The length of instructions are different also. They have different lengths depending on the instructions. So hopefully the instruction set architecture is available. For that, for the reverse, I will use IDA with a plugin from the Mad Inventor, very, very nice plugin from this guy. And I also grab the secureboot.h inside their GitHub, which is listing all the ROM functions. They deprecated since, but now I have all the symbols. And I also call a friend to check my mess. It's always good to have friends. At the end, it's not perfect, but it's clearly doable. I can reverse, and for example here, I display the start of the ROM functions. So I dig a little bit inside this boot ROM, and I locate the functions in charge to check the secure boot and the bootloader. It's called ETS secure boot check finish. And when the results is wrong, it will go to the left side and will print the secure boot check fail we will see on the UART previously. So this is decided by a branch if not equal immediate instructions, and the result will depend on the A10 registers, which is storing the return value of the secure boot check finish function. So my goal, I want the PC to jump to the 400075 C5 to execute the bootloader. So this little instructions is my target now. So it's because I have JTAG access, I will validate this using a little JTAG script. So I use OpenOCD to connect. And then I launch my script to GDB. I wait a little bit, and then we can see we can run unsigned code using a little patch on A10 registers. So now it's time to pawn for real, because in real life you don't have GTAG normally available. And I was not able to find a way to exploit this vuln by pure software. So here, fault injection is my only way. I modify a little bit the previous setup to glitch simultaneously on VDD CPU and also on VDD URTC to have a maximum dropout. And I also probe the SPI MOSI to have a timing information about the frames of the SPI. So the first attempts, they look like that. This is a scope screen. And of course, my previous reverse is helpful to find the timing and the specific windows. I have to insert the glitch. So I will locate here. I zoom inside, so we can see channel 1 is the serial output, providing some printf information. Then we have the SPI frames, and I will glitch just after the end of the SPI frame, okay? Here we can see the glitch was not able to modify the code of the boot ROM, and then we can see the secure boot check fail message at the end. But with a little bit of time, a little bit of modification of parameters, we can see here on this scope screen, the message on the UART has changed. And this, it means the CPU is jumping to the entry point. The bootloader is executed now. So as a POC, from the shell point of view, it looks like that. The ESP32 is in an infinite loop, trying to load this unsigned bootloader. And finally, using a little glitch, I can run my unsigned code. Sorry for the tilt of the image. It was late. So, the conclusion. Secure boot bypass exploits. It's done using a boot ROM vulnerability triggered by fault injections. This is not persistent if a reset occurs, but the good thing is you have no way to fix without ROM revision. I went to responsible disclosure. I sent the POC on June 4. I posted on September 1. Then the vendor provided a security advisory on September 2. They request CVE, and they decide to patch the secure boot mode by enabling all the times the flash encryption. So it means now this attack is not possible, because you will have an encrypted bootloader, and this will not be correctly decrypted by the ESP32, and then your bootloader will not be executed because it will execute trash instructions. For the information, a security lab called the Rescue found the same vulnerability than me. Well, I mean, on the secure boot, my job is done now, and it's why I'm looking for the flash encryption. The role of the flash encryption is to protect the firmware confidentiality, and of course, is to protect against binary reverse. Without flash encryption, it's really easy to extract sensitive data. I did a little bit of work at the beginning of the year about that, putting some light bulbs, Wi-Fi light bulbs. So it was a little job. Firmware encryptions is more and more present today in IoT devices. For me, it's a little bit of security by obscurity, but nevertheless can be efficient. Espressif recommends secure boot with flash encryption for maximum security. So let's review this flash encryption mechanism. Inside the ESP32, we have a flash memory controller, and the flash encryption blocks is done in hardware, doing encryption and decryption inside this flash memory controller. It fetches the key from the fuses, and it also fetches some other parameters, and it decrypts and encrypts instruction and data into caches. And from a software point of view, you cannot access to these particular caches. So here, the flash encryption key is the main asset. It's the IES key used to decrypt the firmware, and it's stored in eFuse BLK1. So I do the same. I set the flash encryption. I burn the flash encryption key inside BLK1. I activated the flash encryption. I flash an encrypted firmware inside. I checked my eFuse map. We can see now we cannot read out BLK1 and BLK2. And the firmware, I dump the flash firmware to verify it is encrypted. So maybe it's not very common to see it's encrypted on this picture, but you can trust me, it's encrypted, and we can see it's ECB because some 16 bytes data can be repeated. So, how to break the flash encryption? I did some tests, and I did not find a particular weakness to access the key by a pure software, and did not find a way to attack by a differential fault analysis, which is a kind of fault injection techniques to attack IES. My last op was a side channel analysis to target the bootloader decryption during the load from the SPI flash to the SRAM. But my setup was a little bit too limited, I think, because SPI bus is producing a lot of noise, and I was not able to control the SPA frame properly, and then to have nice acquisition for my offline treatment of DPA curves. I tried DPA attack, CPA, but I didn't have enough leakage, so I spent 1 week, no results. I was a little bit tired. And I have to conclude on that. And yes, I lost against flash encryption. But I remember to follow some advices. And as Fatal Fury said, if you watch carefully your opponent techniques, you will maybe find these weak points. And it's why I'm going to explain right now, because the weak point was in the OTP fuses. And the OTP fuses is a one-time programmable memory based on eFuses, of course. And eFuses can be programmed just one time, from 0 to 1. Once it is burned, it is over. You have no possibility to rewrite it or to wipe it. The organization of the ESP32 eFuses array is the following. On BLK0, you have ESP32 configuration. BLK1 is dedicated to flash encryption key, BLK2 is dedicated to secure boot key, and BLK3 is reserved for user application, like custom Mac, for example, or some other data. According to Espressif, these eFuses, they are read-write protected, and so you cannot read out or modify once the protection bits are set. And these eFuses array, they are managed by a eFuse controller, a dedicated piece of hardware inside the ESP32. Let's go to reverse a little bit these fuses. And in the boot ROM, I only find two functions, eFuse read and eFuse program. And these functions, they are only used during a special boot mode. And this is kind of interesting for me. The boot ROM never touch OTP values directly. It means only the eFuses controller has access to the OTP. It's pure hardware process, and because the boot ROMs need the secure boot key, this process has to be set before the boot ROM execution. So let's talk about the special boot mode. The ESP32 has a special boot mode called download boot. It's a management mode to flash firmware, to set eFuses, etc. And this can be activated by connecting IO 0 to GND and then to power up. And then we will obtain this message on the UART. ESP tool is the dedicated Python utility to communicate with the previous ROM functions. It has dedicated commands available from UART to deal with the fuses. So you can dump, you can program. It's quite useful. So let's talk about the eFuse protection. Because when you try to dump the eFuses value on a ESP maximum security set, you will obtain only 0. So you can see block 1 and block 2 and block 3 is only 0. But my goal was to identify the read-write protection bit. And this I found here on the first word of BLK0. And these 2 bits here are the read protection bit. But, okay, where is the vul? I have no vul here, sorry. But I know some stuff. I know the boot ROM does not manage the eFuses. I know the eFuse controller has to do the job before. I also have some knowledge about the special boot and also the location of the read protection bit. My goal, my idea, is to glitch the eFuse controller initialization to modify the read-write protection. And then I send the dump command in special mode. I read out the BLK1 and BLK2. So I call that fatal glitch. Then first I have to identify this hardware process. I do that by a simple power analysis. And then when I zoom a little bit inside this process and I glitch at this very specific time, here we can see the power consumption, channel 3. The results of the glitch during this activity is the following. And this is a secure boot key and flash encryption key extracted from eFuses, from a maximum secure ESP32. So when you obtain that, I mean, you're quite happy. But sadly, the dumped keys, they are not exactly true values due to the glitch effects or due to the design of the eFuse array. And I know that because I burned the keys, so I know the value. So I have to do some offline statistical analysis. So I repeat 30, 50 times the attacks to obtain a set of dumped keys. And I just keep the most recurrent bytes. Here is for secure boot key analysis. And finally, in the worst condition, I have to brute force 1 byte of the IS-256 key. It's not so bad. It's the same for flash encryption key. And I mean, 1 byte brute force, it's not a problem. So here's the full fatal exploits. First, we have to decrypt the firmware. You dump the encrypted firmware using the download mode or by dumping the flash directly. You perform the fatal glitch to extract the keys. You run the statistical analysis. And then you have to confirm the true flash encryption key by decrypting the firmware. Okay? So you set the script, and when you obtain a decrypting firmware, you know the key you have used to decrypt the firmware was the good one. We have to respect the byte orders in the binary file. It's completely different than the byte order in the eFuse array. So, yeah, it's just a remark. And then now firmware is now decrypted. I know I can extract the first 128 random bytes located at 0x0 in the decrypted firmware. I also extract the bootloader at address 0x1000. And then I confirm the true secure boot key by computing again the digest. So here is the initial digest located at 0x80. And by using a digest secure bootloader command, once and the keys, when I obtain the same digest, it means the secure boot key I have used for this specific command was the good one. Now I know the 2 keys. I can write my code, maybe a little firmware backdoor, I don't know. I compile using a flash encryption key and a secure boot key. This is totally transparent now and set by the framework of the vendor. I flash the new firmware, and it's done. So, about the conclusion of that, it's an exploit leading to secure boot key and flash encryption key extractions. You break secure boot and flash encryption because it's based on symmetric crypto. An attacker can decrypt the firmware and access sensitive data, can access IP, can access user data. An attacker can sign and run his own encrypted code persistently. So good luck to detect if the firmware was modified. It's low cost, low complexity. If the keys are not unique by devices, you can have a nice trouble. It's easy to reproduce, I think. No way to fix. And all the ESP32 versions are vulnerable. So vendor's reaction, responsible disclosure, of course. I sent the POC on July 24. The images we have previously seen. Requested a CV for me, and then I post on November 13. And it was nice because they published a security advisory on November 1. So, I mean, they learn since the first communication between us. They are more reactive. I mean, it's kind of nice to see that. So in their security advisory, they say they have no solution, but you can buy the next version of the ESP32. It's not so bad for business. But yeah, still millions of vulnerable devices on the field for the coming years. The impact for hobbyists, I mean, don't worry, your connected device is safe. It's not a problem for you. For the developers, in case you are using ESP32 security feature previously attacked to protect your secrets, I mean, you should be a little bit worried maybe. For your information, I identified 3 companies using ESP32 flash encryption and secure boot in their product to protect their business model. I will not tell the name of this company. For the vendor, it's forced to modify silicon to save his longevity commitment and his reputation. And yeah, I just have a question about current devices offered for sales. So final conclusion now. An attacker with physical access can compromise ESP32 security badly. It's persistent bypass of secure boot and flash encryption. So fix, no fix. Platform is broken. A new chip version will be released. For me, it's the end. A little general message for vendors. So don't patch silently. Don't patch silently, security researcher. It's not elegant. It's not a good technique. New results coming soon, of course, so stay tuned. Reference and credits here. Thank you. So if people have questions.
How long does it take until it actually glitch and you manage to success to actually bypass? It's not in the first try, I guess. If I'm trying, how much time should I let it run until I get the result?
I mean, here I was in the identification process, so it takes me a little bit of time. But now, with this presentation and with the blog post, you can reproduce very easily because you have the timing. You have the width of the glitch. You have the setup. I mean, even for a proficient hacker, I mean, in 1 week, he can reproduce this attack. I'm pretty sure about that.
No, the question was, if I try, for example, I have some devices and I want to hack it, how much time does it take if I have a production line to hack that? I have to keep it for how long until I manage to? You said I can glitch every time in the first try? Because usually the power glitch, you have to try for multiple times until you actually get results.
Yes, because you have to try multiple times because you don't know the specific parameters of your glitch.
Okay, so if you have it, you can do it almost every time.
And with this presentation, you can find a lot of information. So this will speed up your process.
Okay, thank you very much.
Welcome.
Hi. Very nice, Richard. Thank you very much for presenting it. It was super good. Do you know if the new ESP32 S2 is vulnerable too, or that is the new version that they fixed?
I mean, you should probably contact the vendor for that, because I have no information, and I'm pretty sure they don't want to send me a ESP32 S2 for evaluation, so you should contact them.
Thank you for the talk. I wonder, when you do voltage glitching for the encryption, did you got any faulty ciphertext?
Can you repeat, please?
When you do glitching to the encryption,
Yes.
like the encryption core, did you get any faulty ciphertext?
Yes, yes, of course. You have a lot of faults. You have to sort, to filters, and then depends on your on the algorithm you try to attack. Depends on what you want to do. Yeah, you can use or not the different faults. Some faults are more useful than others.
Yeah, I mean, you said you get some ciphertext which is the same as the plain text. That
Yes.
means the encryption doesn't execute.
Yes.
So did you get any faulty ciphertext which is different than the plain text?
Yes, of course.
Okay.
But it depends on your timing.
Okay.
Because, of course, if you are going to glitch the computation of DIS, yes, of course, you will have faulty ciphertext, and maybe you will be able to do DFA, for example.
Yeah. Okay. Thank you.
Welcome. So, thank you.